Good morning, good afternoon, good evening, depending on where you're watching from. This is Don-Electro-Tech. We are responsible to bring to you some of the WAEC, JAMB, and other external exam related questions. Now, we are going to be talking about calculating number of molecules of water of crystallization. This is one of the questions also witnessed in chemistry practicals. Like I told you, as a student, you need to subscribe to this channel so that you can get more of these solvings. Because WAEC is here to release the yellow paper, and we have been doing random samplings of these questions, where some of these questions that we are going to treat here, I bet you will see most of them. So you just have to follow up, because the question is not far from what you are seeing here. Exactly what you are seeing, it only figures will actually change, or some of the reagent will change. But this is the procedure in solving some of these questions. There is no two ways about it. Bet me, you will always see it like this in the exam day. So I will advise you to subscribe. Tell your friends to come to this channel so that you could learn new things. I'm also coming up with chemistry and physics practicals that will also help you. Some of you students don't know how to plot graph. They have been going about making mistake in plotting of their graph and slopes, calculation of slopes, and we are going to treat all these things here. As you come to this channel, I bet you that your exam is going to be a perfect one. I bet you that, because this year WAEC exams is going to look something different, because like 4 top subjects will not have the same questions, as there will be a variation of questions among the students. A student in 001 will not have the same question of 002, 003, just like that. So it's going to be like more of a jam question, especially English and mathematics. So I will advise you to work on this. Try to achieve this at the end of the day. Now we are going to talk about calculating the water of crystallization, calculating number of molecules of water of crystallization. And what is water of crystallization? Water of crystallization, like we likely said before, when salts, like some salts, are crystallized out of aqueous solution by cooling the hot saturated solution of the salt. These salts are associated with definite number of molecules of water, molecule called water of crystallization. The salts are referred to hydrate salts. When these salts are heated, they lose some or all the water of crystallization to the atmosphere, and the crystal structure will collapse and they become powder. The powder form is called the anhydrous salt. So now we are talking about the salt of water of crystallization. Now some salts are crystallized out of aqueous solution by cooling the hot saturated solution of the salts. These salts are associated with definite number of molecules of water called water of crystallization. Thank you too much. And we are going to be giving some of these examples that relates to water of crystallization. Like we have, for example, we have sodium. You can see that we have sodium carbonate. We have sodium carbonate. We also have copper triosulfate, 6-pentahydrate. We have sodium triosulcarbonate decahydrate. These are water of crystallization, because they contains what is called water. But this can also be, water crystallization can also be removed by undergoing some fractional some separation techniques, which is also involved in getting what is called anhydrous water. So that is how we are going to get into that area of practical. Now, without wasting much of our time, now let's go into the practical to calculate number of molecules of water of crystallization. Let's take this example we have here. We say that B is a solution of sodium carbonate and water, M molecule of water, prepared by dissolving 7.150 gram of the hydrate salt in 250 centimeter cube of the solution. Solution A was prepared by diluting 50 centimeter cube of hydrogen chloride acid containing 2.0 mole per dm cube of hydrochloric acid to 500 centimeter cube. Now, number 1, put A into the burette and titrate with 20 or 25 centimeter cube of the portion of B. Using methyl orange as indicator, full stop. Record the volume of your pipette. Tabulate your burette reading and calculate the average volume of acid used. B. From your result and the information given, calculate 1, that is I, the concentration of acid in mole per dm cube, concentration of B in mole per dm cube, value of N in sodium carbonate and water, and percentage of water of crystallization. The equation of the reaction is given, and this equation, we can say that the equation is either balanced or imbalanced equation. At the end of the day, we check whether the equation is balanced or not balanced. Now we have some of the atomic mass of these atoms that you see there. We have carbon equals to 12, oxygen equals to 16, nitrogen 23, and hydrogen is 1. Now let's go into the solution of these problems. We are going to solve these problems. So now we have these problems to be solved. You check a look at this question. I would advise you go all along with your paper and pen to copy out the question and follow the solving procedures as you can picture from this video. Thank you very much. Now let's assume we just did the practical like we have been doing before. We just did the practical as we have been doing before. We have to tabulate our values. If you watch that question, we said the question said we should tabulate what? The values, the table of values. You see, there's a put A into the burette and titrate with. We are going to use the volume of acid used. So the volume of base used is through the pipette. We are going to draft out the table, and so that we also follow up as we have been doing before. Some of you that have been following up this class, you understand what I'm saying. You understand what I'm saying. So you need to have the table of value. Just say this is our table of value. Table of values. Table of values. Our table of values. Table of values. We have the table of values. Now let's say the burette reading. This is the burette reading. The burette readings. The burette readings in centimeter cube. We have the final reading. The final reading in centimeter cube. These are the unit of volumes, and the volume of acid, volume of base used. Volume of pipette. The volume of the pipette. The volume of the pipette used should be. We are using 25 centimeter cube pipette. We are approximately 0.025. Sorry, which is the same as 0.025. This. So this is volume of pipette. The this thing used. The indicator. I want to talk about the indicator. The indicator used. Indicator is methyl orange. Indicator is methyl orange. Methyl orange. That is the indicator. That is the indicator uses methyl orange. Now we have the indicator as methyl orange. So you just watch very well. Whether is methyl orange. So we have this our table of values. Our table of values. Burette readings. This is the initial. The initial readings. The volume of the volume of A, volume of the volume of B, the volume of B or A. Let's say the volume of A, which is the acid, the volume of A used in centimeter cube. So we have what is called the rough reading. The rough reading. The first reading. The second reading. So when you have this is your table of value. This is our table of value. We have this our table of value. So we're just assuming. I told you we are just assuming this reading because we are not in the lab. We are just assuming that this is what we are going to have at the end of the practical. We are going to have at the end of the practical. This should be our endpoint. First reading 20 is the first reading. The initial reading is at this point. We have something like this. So this time we have 42.30, 17.70, and 24.60. So this is going to give us this first second reading. How did we get this? The initial reading is where the burette itself, the burette, we are going to see this things in lab. That's why I say you should follow up. You need to follow up these practicals so that you understand how we got these readings, how we are getting this reading. This reading, we got it from something. That means from the main practical when we are titrating the acid and base. And at the particular point where we want to call the end points, a particular color change is being observed. And that one color change is observed, we check the volume in the burette where the acid stopped. And the volume of the base is already defined, which is the volume of the pipette. Is already the volume of the base. So the acid volume is what we are going to determine by making this by doing this practical repeatedly, either 2 to 3 consecutive times to achieve this. So at the end of the day, when you get this, the initial value, which is the initial reading, when you subtract the initial reading from the final reading, you have that means 225.80 minus 0.75 will give us this. This minus this will give us this, and this minus this is going to give us this. So at the end of the day, we'll look for the volume of what? Acid used. The average volume of acid. The average volume of acid. The average volume of acid used in this question. Therefore, we'll now check the average volume of acid. Average volume of acid. Average volume of acid used, which is VA, is equals to the first reading plus the second reading we divide by 2. Why are we using 2? Because we did the first and second, which is 1, 2. So this is the rough reading. I'm now putting the rough reading in terms of checking the average volume of acid. If we have extra third reading, we also do it the same way. So that means the first reading, the volume of the first reading, the total volume, which is called the titrates. The titrates is what we are looking for. So that is 24, which is equals to 24.7 plus 24.6 divided by 2. So this value now is going to give us let's check this value. 24.70 plus 24.60 is going to give us 49.30 divided by 2. Divide this 49.30 by 2. We're going to give us, which is VA. We're going to give us VA. Divide this by 2. We're going to give us VA is equals to 24.65 centimeter cube, which is equivalent to the same, which is the same thing as 0.02465 dm cube. So this is the volume of acid. That is why I say average volume of acid. From the question, you say we should what? Tabulate your readings and calculate the average volume of what? Acid. Tabulate your reading and calculate the average volume of acid. So this is the tabulated reading. Tabulate your readings and calculate the average volume of acid. So you can see that this is the average volume of acid that we have gotten from that question A. So this is the average volume of acid. It's very, very important. Now the second question there is from your result and information given, calculate the concentration of A in mole per dm cube. Concentration of A in mole per dm cube. Concentration of A in mole per dm cube. Now, when you want to check that, we have from BI, we will now say concentration of A is equals to Ca in mole per dm cube equals to Ca in mole, this is the unit, mole per dm cube, now of acid, which is hydrochloric acid, hydrogen chloride. Now, to obtain the concentration of A, to obtain the concentration of A, Ca, of solution A, used. Use the dilution formula, or the dilution formula. That formula is C1V1 is equals to C2V2. This is formula we use in diluting concentration of a particular this thing. Now when we have, therefore we are saying that we are C1 is equals to initial concentration of A, which is equals to 2.0 mole per dn cube, and V1 is equals to initial volume of A, which is equals to, from that question you see initial volume of A. From the question we have initial volume of A, which is this dilution. Say solution A was prepared by diluting this of hydrochloric hydrogen chloride. So that is what we are looking. This is the volume. The volume there is 50 centimeter cube, which is something at 0.05 dm cube. Now C2 is initial concentration of B, of A, not B, that is the final, the final concentration of A, which is not given. We are looking for the final concentration of A. Then V2 is the final volume of A, which is the acid, which is 4.65 centimeter cube, or I think no, is that correct? That should be no, this is not what we are looking for here. That is not what we are looking for. We'll look into the question. You will see that we have this one. This is what we are talking about here. This is the final concentration of this, which is this one. So we have a 500 centimeter cube, which is equal to 0.5 dm cube. 0.5 dm cube. So with that we continue our solving by checking these values into the given formula. Therefore, when we say that C1 is equals to 2.0 mole per dn cube and C2 is not given, V2 is 0.5 dn cube, and V1 is equals to 0.05 dn cube. So at that process, we now bring the formula back. C1 V1 is equals to C2 V2. Anywhere you see V1, you put C1, you put this value. Anywhere you see V1, you put this value. Therefore, which equivalent to 2 times, which is this 2, this one times V1, 0.05 is equal to what is C2. Our C2 is not given. We are looking for the concentration of A times our V2. What is our V2? 0.5. Therefore, C2 is equals to 2 times 0.05 divided by 0.5. This is going to give us C2 is equals to 0.20 mole per dn cube. So this one is for the I. We have done for the I, which is concentration of A in mole per dn cube. Now the next question there is concentration of B in mole per dn cube. Concentration of B in mole per dn cube. Concentration of AB in mole per dn cube. How do you come about this one? So the way you can go about this one is B. This is B2. B2 will now say that the mole ratio, I've told you put mole ratio, how to get the mole ratio from the equation. From the equation is 2:1. How do we get 2:1 as the mole ratio? Now look at the formula here. Look at the formula. Here, this is the base, this is the base, and this is the acid. So the mole ratio here is 2:1. The 2:1 is that we're talking about acid. The mole of acid there is Na is to Mb. So our Na acid, the mole here is 2. Look at 2 here. We have 2 here. Look at 2 here. We have 2 here. So because 2 is in this acid, as here, this is the 2. Here is this is the molar. This is given here is the mole, number of mole of this acid. This compound here is this. Here now we are not having any further. That means we are is on same one here. So here becomes 2, and here now is 1. So that's how we get the mole ratio. Then using the formula, using the formula to check this, using the general formula, that's a CAVA all over CBVB is equals to NA all over MB. So when you are solving this problem, you now put the values, because already our CA is given. What is our CA now? Our CA is the value we already gotten from the calculation we did here. Let's make clear it. This C2 here, the C2 here is also noted as our CA. It's also noted as our CA. Yes, this C2 is our CA. So the CA there we are looking for, we've already gotten the concentration of acid, which is our CA. So therefore C2 is equals to CA, which is 0.02 mole per dm cube. Now since you have that, now we are checking for what? CB. We don't have CB, that's what we're checking for. So therefore CA is 0.20 times VA is volume of volume of acid, average volume of acid. Look at it here. This is the average volume of acid. So that is our distance. So we use that, which is equal to 0.02465 times, all over is over CB is not given, times the volume of base is what we have from the pipette. The volume of the pipette is the volume of the base. Look at it here, which is the volume of the pipette is the volume of the base. So we also record that volume of the pipette, which is 0.025 is equals to, then NA is what? 2 over MB is what? 1. NA is 2. Look at it here. NA is 2. This NA, this MB. So NA is 2. So you put 2. When you see you put 2 over MB, which is 1. So you cross multiply, then you cross multiply. This multiply by this. So you have CB times 0.025 times 2 is equals to, this one will go 1 times 0.20 times 0.02465. So here we have, after multiplication, we have a value here. It's going to give us CB is equals to 1 times 0.02 times 0.02465 divided by 0.025 times 2. So when you have these kind of values, you need to check one or two things. Therefore CB, we assume that after calculation and all that thing, you'll get a value of so I don't know, we have 1 times this will give us 0.00493 over, this is going to give us 0.50. So at that point we'll now divide this, divide by 0.050 is equals to, this is going to give 0.90986 mole per dm cube. So that is how we solve that. Now the next stage of this question that we have here is the value of N in sodium carbonate and water. That is we are seeing there is sodium carbonate. Sodium carbonate, you know what it means, that is some molecules of water in that sodium carbonate. So we are going to check their value. Therefore we have number 3 to calculate the value. Therefore we have the molar mass of sodium carbonate is equals to, sodium is 23, therefore 2 times 23 plus, because this is 2, sodium is 23 already. Check these values here, you see that sodium is 23 here. So that is when 23, now we have 23 here. Anyway, it's going to put 23 times this 2 that is here. Carbon is 1, which is 12. So we now say that this is plus 12 plus 16 times 3, because oxygen is 3 here. So 16 times 3. So the whole of this thing is going to give us, after adding, we have 46 plus 12 plus 48. It's going to give us 106 gram per mole. So that is the molar mass. Therefore molar mass of sodium carbonate and of water is equals to Now you have to apply this principle. By applying this, we will now say that the only this one gave us this value, so we'll now put 0.6 plus. Now we check here, n bracket hydrogen is 2, isn't it? So it becomes 2 times hydrogen. So hydrogen is 1, so 2 times 1, the molecular mass of hydrogen, atomic mass of hydrogen is 1, so 1 times 1 plus oxygen is 16 here, so you put 16. So the whole of this give us 0.6 plus this n is multiplying everything inside this bracket. This time it gives us 2 16. So here 2 plus give us 18. Is 0.6 plus this is going to give us 18 times this give us 18n. So here is 18n. So at that point we are having 18n here. Then we'll now go for mass concentration of an hydrous salt is equals to molar concentration multiplied by molar mass, which is same thing as molar concentration multiplied by, our molar concentration is already given, which is this value here. So we'll now put this value as 0.0986 times 0.6. This is going to give us 10.388 gram per dn cube. Now that is what we have there. The mass concentration of hydrate salt, because the salt contains water, which is the hydrate salt, is equals to mass m all over volume v. Therefore the mass of this thing is given from that question. What is the mass? Look at the mass here. This is the mass of the salt. This salt contains water, and this is the mass. So we'll now say that the mass is going to give us that mass now is going to give us we have 7.150 divided by the volume. What is the volume that was contained in that question? The volume in that question is this. Look at the volume. So the volume there is this thing. So after conversion, you convert it 0.250, because how do you get 0.250? We did that by 250 divided by 1000. This is in centimeter cube. To convert it to decimeter cube, you divide by 1000 to give us 0.250 dm cube. So that is how we got that value there. Now at the end of the day, we are also progressing, we are moving forward. Now we have a solution of this value, where we will now say that this divided by this is going to give us this value now is going to give us 28.60, which is therefore which is equal to 28.60 gram per dn cube. Now continue solving. We have the solution now. Therefore, to have the value, the number of that value, and the value of n, mass concentration of hydrated salt, hydrated salt, we divide by the molar mass of hydrated salt is equals to mass concentration of anhydrous salt all over molar mass of anhydrous salt. What is anhydrous salt? Like I told you before, that some salt are crystallized out of aqueous solution, or by cooling the whole saturated solution of the